Having used the force on a length of wire that carries current, in class you derived the behavior of a loop of current in an external B field. We want to lay out some rules now which will connect loops of current, or things that can be modeled as magnetic dipoles, with a familiar everyday object, the bar magnet. Usually we label these bar magnets north and south, one on each end. And if you mapped the magnetic field of a bar magnet at any point in your career, you would see these lines which circulate outside of the magnet. We have rules for magnetic field now. B. Those magnetic field lines are pointing away from the north pole of the magnet and towards the south pole of the magnet. Inside of the magnet, we follow the second rule, and that is that magnetic field lines have to form closed loops. So inside the magnet, those field lines are actually pointing from south to north, but don't let that confuse you. When you are outside, they always point north to south, and they must circulate, forming a closed loop. When you do the basic experiment as a child, you take two bar magnets. If you put the north of one magnet next to the south pole of the other magnet, you obtain an attractive force. If you do the other experiment where you place the south pole of one magnet near the south pole of the other, there is a repelling force. If we treat this first magnet here as the source of some external magnetic field, be external, it points this way in this vicinity towards the south pole, following our rule, then you can see that these individual bar magnets, they want to align themselves such that their vector from south to north is aligned with the external field. This is the position where the bar magnet would like to be in. So we could say it's near its stable equilibrium, while this bar magnet is very near an unstable equilibrium. This vector now pointing south to north is anti-parallel or opposite the external B field. That is the most unstable configuration, and you know that when you take those two magnets and put them together and maybe let one of them go, it's going to flip quickly. Maybe if they're strong enough, it'll flip around and they'll reattach here, not north to south. What we want to do is define these vectors as the analogous magnetic dipole moment vector mu to the one that we defined with current loops. So a bar magnet behaves in the same way as a current loop. We can model it as if it has a dipole moment vector mu because it creates the same sort of dipole magnetic field. We saw with the Helmholtz coil setup that if you flow current in a loop, it creates a strong magnetic field proportional to the current that's coming out of the page here if the current flows counterclockwise, out of the page in the center of the loop, but it must wrap around up out of the page and down into the page out here in a closed loop. If you looked at that from the top of the loop instead of from the side, what you would see is these circulating lines of magnetic field produced by the coil. And what that gives you is a dipole moment vector from the right-hand rule pointing from the effective south pole of that dipole towards the north pole. Remember, the right-hand rule tells you to curl your fingers in the direction of current, and your thumb, which is out of the page here, is in the direction of the dipole moment vector. So with these rules of opposite magnetic poles attracting and like poles repelling, you can see then that dipole moment vectors as models of the physical objects will do the same, right? A dipole moment vector wants to naturally align with the external B field. That should remind you of the electric dipole moment vector P, which will tend towards alignment with an external electric field E. The pattern is exactly the same. All of the rules about torque and potential energy will hold. So in class we discussed that the magnetic dipole would feel a torque in an external B field, and it represents potential energy U, which is the negative dot product of mu dot B, just like we saw for the electric dipole. If this stack of neodymium magnets is acting as the source of our external B field, you can see here our MagneProbe, small bar magnet, is responding to that field. When close to the North Pole, it aligns with its blue South Pole end, close to the north. You can see it's tracing the path of the external B field. It is aligning with that external field. Now the red side is pointing down the page. And as we come back around to now the south side, the North Pole of our little mu vector model here, our physical mu vector, is attracted to the South Pole of the strong bar magnet. So in class you use these MagneProbes to model the magnetic field created by a loop of wire carrying current, and you can see that that field is extremely similar in its nature to the field of a bar magnet.